Okay, good afternoon. My name is Neil O'Brien. I am a senior cloud architect at the Communications Research Center, CRC, which is under ISED, Innovation, Science, and Economic Development. My main role at CRC is to oversee all things cloud, be it networking, architecture, security, basically to ensure that CRC has a unifying vision for all of our cloud deployments. My co-presenter is Sarah Dumoulin. She is one of our senior data scientists, and while her area of expertise is broad, lately she's been focusing on geostatistical analysis of communications data. So today we're going to be discussing how CRC used Sarah's work to help the Public Health Agency understand how Canadians were moving around and isolating during the COVID-19 pandemic. Also, we're going to be touching a little bit on the different cloud architectures that we used to enable Sarah's team to move as quickly as they did. So with that, I'm going to introduce our presentation. We call it From Communications Research to Public Health, Pivoting in the Cloud to Address COVID-19. Okay, so just like everyone else, the pandemic was declared on March 11th by the World Health Organization. On March 13th, ISED issued work from home orders for the entire sector. And amazingly, the first business day back, March 15th, CRC employees were back working as if nothing really changed for us. It was a simple switch to us. And then the next 2 weeks moved really quickly. CRC deployed an environment for Public Health Agency to work in CRC's cloud. And on top of that, CRC was generating daily COVID-19 mobility dashboards based on terabytes of data. So this was all pretty fun and amazing stuff. So how did we actually get to a point where we can move this quickly and do this kind of stuff? So I keep hitting that. So to kick this off, I gotta first introduce CRC's virtual research domain. So some of you may be familiar with this already. This is our cloud environment where our researchers do all their compute. I'm going to talk a little bit about its features first. So main feature is obviously that it's multi-cloud. We have it connected to the AWS and Azure environments. We also dabble in the Google Cloud platform, and so you're going to hear a bit about that in this talk. Another feature is that we do a multi-account structure, particularly in the AWS environment. The main reason we do this is to isolate different environments. So we can isolate our core services from our development environment, and we can also isolate collaboration environments. And we've done that in the past with Environment Canada and climate change, as well as with Public Health Agency. Under the account structure, we have a network architecture that's shared across the different accounts. This is an ITSG22 based network with segregation for different zones and public zones. In that, we have isolated zones for core services. We also have isolated network zones for researchers and for collaborators. And basically the idea is once a researcher is in one of those research zones, they have almost unlimited network access within their zone. So they have lots of agility within their zone, and there's a fair amount of control of how we access the different zones. In front of all that network architecture, we have what we call a strong front door. So that's our blazingly hot firewall. On that firewall, we have full antivirus, anti-malware, URL filtering, like the whole 9 yards. And the whole idea is that we want to keep everyone out, but once you get in, you're going to have access to the full suite of cloud services and I'm not going to say unlimited, but open access to a lot of the other services that are there. And I guess lastly to mention is to connect to this system, the VRD, all connections are done with multi-factor authentication. So like on top of the architecture, another really important piece that I think is sort of the unsung hero of how CRC is able to operate is our cloud governance framework. So really what this does is this is a framework that describes how CRC operates in the cloud. It describes roles and responsibilities for deploying, maintaining, and monitoring cloud services. One really important element of the framework is how we manage projects and budgets. So we have full visibility on how a project is spending its budget and on what services it's spending, and we can watch during excuse me, during the life cycle of that project in near real time to see how the spend is going. What's really great about this is it gives us the visibility, but it helps us manage the pay-as-you-go model of the cloud, and it allows us to make changes to our budget sort of on the fly, and allows us to do pivots like we're going to talk about in today's presentation. The last piece the government does is it really takes the decision making and pushes it down as far down the chain as we can. So once a budget is approved, a user can take their cloud resources and spend their budget any way that they want. So we don't restrict what users can do once their budget is approved. As long as their budget is on track, which we monitor vigorously, they have the freedom to build what they want in their restricted zones. So we give them access to the zone, we give them access to their budget, and then they can basically do whatever they want. And this really has given our researchers a lot of agility and a lot of flexibility on things they can do. So the last piece I want to say about this is this architecture and this framework we think is really designed to enhance discovery science. This is a very different sort of philosophy for deploying cloud than say an operational or like production type environment. This is not that. This is for exploring and discovering and building. So back to the story. With all this in mind, how did we go from the pandemic to working right away? Well, we had a cloud environment already, and this is a very simplified version of what the architecture looks like. But basically, the idea is we were working from from on-prem in CRC. When the pandemic hit, instead of working from CRC, we started working from home. So we just allowed access from different spots. We still had multi-factor authentication, and you go through our firewall and then you can access your VM. Once you're in your VM, you can now access all the different tools and all the different data sets and all the different clusters that we have within our VRD. So, and like I said, this was already set up. So once the pandemic hit, it was just flipping a switch and people could work from home, and that was really cool. We felt after the pandemic hit that since we were able to work from home so quickly, we recognized that we had something special, and then not every government department was able to make this change as quickly as we did. So we sent an offer out to various other research departments and offered a cloud environment for them to work on. Of the various responses we got, Public Health Agency asked if we could set up a cloud environment for them, and that's what we did. So we were able to take our cloud environment and because we're using best practices like infrastructure as code and guardrails and whatnot, we were very quickly able to duplicate a new environment for them, their own VPC, their own account, and then create network access rules that they were then able to go into their environment, not interfere with ours, and just start building tools and or exploring. And they did that. And so within days, we had this environment up. Within a week or two, we had p-hack users who had deployed VMs and they were doing COVID-19 modeling. They had a Twitter scraping tool that was scraping Twitter and then analyzing the data. And there was about a dozen users in there. And so that was a very fun project. Okay, so with that project in mind, moving on to the next one, we're going to start talking about how CRC's own work changed when COVID hit. So I'm going to pass this off to Sarah, and she will talk about that.
So when COVID hit, of course, all the data science team were sent home, and we started working right away in the cloud. Luckily, all of our data and everything was in the cloud, so we were able to start working right away. And at that time, we were already working with a crowdsourced data set that was collected from mobile phones. And this was for research that we were doing in the department for telecommunications. So we were using an anonymized data set collected from about 250,000 users throughout Canada in order to do things like look at which Canadians were underserved or to understand patterns underlying spectrum demand. So the map I'm showing here on the right is just a map showing average Wi-Fi speeds that was derived from that sort of crowdsourced data. So after COVID-19 started sort of hitting different countries in the world, we began to hear stories about this sort of crowdsourced data being used by epidemiologists and policymakers to study human interaction. And this is because, sort of as we all know by now, COVID-19 is primarily spread through human-to-human interaction. And by examining crowdsourced data from mobile phones, you can construct what are termed as mobility measures. In other words, looking at how far people move and where they move to. And by looking at how far people move and where they're moving to, you can try to link that sort of movement to whether or not disease is spreading. And you can also try to monitor whether or not people are obeying sort of shelter-in-place orders or shutdowns that have been imposed by public health. You can also use this sort of data to try to predict where the next hotspot will be. If you see that groups of people are moving from one place where there's been an outbreak to another place, well, you may want to warn the public health officials in that second location that you may have COVID-19 activity in that second location. So when public health came to us and asked us to whether we were able to help them with the COVID-19 outbreak, we sort of quickly looked at what data we had available to us. And we realized that the crowdsourced data that we had been used for telecommunications purposes could be used for mobility, even though it had not originally been intended to do so. What we realized was that the data samples we were receiving from the crowdsourced provider were triggered by user movement, and that each of those samples came with a latitude and longitude reading. And because of those two factors, we could use that data set to make these sorts of mobility measures to measure how far people had moved and where they were moving to, even though that data set had not originally been collected for that purpose. So we set to work, and the first set of mobility measurements we started to build were what's called relative mobility. Well, so when we talk about relative mobility, what we're talking about is how much mobility has changed. And in this case, what we were particularly interested in understanding was how much mobility had changed from the pre-COVID period. So if you take as a baseline or as your sort of normal mobility, the mobility in this case between, say, January and the end of February of the year, then you can compare and say, well, has mobility increased or decreased since that period? So if you look at the graph on the bottom left of the slide, you can see what's called a sort of a heat map. So the color represents how much mobility has changed. And in this case, sort of a middle green color indicates that it has not changed, that it's at baseline, it's at the normal level of mobility for pre-COVID. And a dark blue would indicate a big drop in mobility, and a light yellow would indicate a higher than average level of mobility. So this chart goes from January to sort of the end of March of 2020. And it's a chart for all the sort of major cities in Canada. Not all of them, but most of them. So what's interesting in this is that you can see sort of patterns even before COVID, that on weekends, for instance, you tend to have lower mobility, which makes sense. You're not going to work on weekends, so people are slightly less mobile. And you can also see this really big dip in St. John's over the January 19th period, where they had that big snowstorm. So obviously their mobility was reduced because they were stuck inside due to the snow dump. But then you can look after March 15th, so after people the provinces started closing down a lot of workplaces, you can see the huge reduction in mobility really across all these major metropolitan areas. So they're reducing mobility up to almost 60% in some of these areas due to the sort of stay-at-home advisories from public health. So you can see that some of these areas are not staying home quite as much as others. So Toronto, Vancouver, and Victoria in this chart are slightly lighter than the ones among than their neighbors, while Ottawa seems to have done a slightly better job at staying home, and as is Montreal. So we did other mobility measurements, including relative mobility between regions and major cities. So that would be mobility between sort of Vancouver, Burnaby, or between provinces. And relative activity at points of interest, such as gyms or grocery stores, airports, and hospitals. So that's looking at has the activity at those places changed? So if you have, we were expecting, for instance, that after we had closed down gyms and closed down coffee stores, that the level of activity that we would detect at those environments should go down drastically, and that is indeed what we saw. For things like grocery stores, people were still going to grocery stores, but they had been requested to go there, only once a week rather than many times a week. And we also were interested in knowing whether or not they had changed their behavior as far as spreading out the time of day people were there, so there wasn't quite the same peaks of people going to the grocery stores, or whether they had changed the day of the week they had gone, or whether they were spending as long in the grocery store as they used to. So we would look at what was called dwell time, or the average time spent at points of interest. And that's what I'm showing in the graph in the lower right here. So this is the median dwell time, the median trip time, basically the time that we detected people were in grocery stores for various provinces. This is over the time frame of March to the end of May. And you see a sort of bump where red here indicates a longer time in the grocery store, and you can see that there's a sort of increase in the week around just before Easter, which is not super surprising. I guess people still wanted to get their Easter dinners. They spent a little bit more time grocery shopping that week. So once we started producing all these graphs and all these indicators, we wanted to be able to update them every day because we were getting in new crowdsourced data every day. But of course, to do that by hand every day would have mean a lot of work. Luckily, we were in the cloud, and the cloud allowed us to develop sort of automatic pipelines to create these graphs and tables without any intervention on our part. So BigQuery was the SQL query environment that we were using, and BigQuery has the capability to schedule queries. So we would schedule queries that we had developed to run early in the morning. And then we would write Python scripts that would fetch that data, do any post-processing we wanted done on that data, and then create the plots and tables from that data that would be then sent to an S3 bucket or similar. And then any web page or Shiny would pull the data from there. I originally did this by loading it up on a cron job on a VM, but then we moved it into AWS Lambda, so I wasn't paying for that VM all the time. I was just paying for the compute on AWS Lambda when it was required. So after 2 weeks, so by the 1st of April, this is the sort of dashboard that we had produced. We would have this was a dashboard where public health could click on any particular province. It would show the number of cases, new cases for that day, and it would give you at the bottom the relative mobility for that province and the major cities in that province. And in the top left here would tell you the total cases in that province, the new cases today, the active cases, and the number of people who had been deceased in that province from COVID-19. On top of this dashboard, we also had another web page that would display this sort of interregional mobility graphs and the point of interest graphs that was also automatically updated. So both of these were automatically updated every day so that public health could view them if they wanted to, and that was all done sort of within the space of a couple of weeks. So after we'd done that work with the initial data set, we sort of realized that we had some limitations and we wanted to sort of branch out to get different data sets. In particular, the initial data set, as I mentioned, was not collected with the intent of doing mobility analysis. And in particular, they had a end user license agreement that people signed when they were agreed to have their data collected. That was restrictive, that meant that we could not do the sort of analyses of outbreak analyses or looking at user movement over longer periods of time that we wanted to do. This was also due to the fact that user IDs were not persistent. So we had user IDs in that data set only lasted for a day. And if we wanted to look at movement over a longer period of time, it was just not supported there. Also, the number of daily users, while 250,000 users sounds like a lot, the number of users was highly concentrated in, well, not highly concentrated, but it was concentrated in Quebec and Ontario, that we had fewer users in the territories and in some of the eastern provinces, and therefore it was more difficult for us to draw conclusions about movements in those areas. And it was also more difficult because of the number of users to draw conclusions about areas that were more remote or sparsely populated. And so we decided to investigate the possibility of obtaining further data sets to augment our capabilities. So we looked at various other crowdsourced providers and looking primarily to find denser data, so more users every day and more persistent IDs. And that led us to what we're going to call provider number 2. And the provider number 2 data had a larger number of daily users at about 400,000 per day. It had persistent user IDs that lasted throughout the life of the data set. And that meant that we were able to use it for a larger variety of analyses at a smaller geographic level and analyses over time. So I'm going to give it back to Neil now.
Okay, so I just want to interject here and talk a little bit about the cloud architectures that enabled us to move quickly here. One of the great things about us being in the cloud is that if we work with a third-party provider that is also in the cloud, it is very easy for us to access the data. So typically or historically what you would do, getting large data sets like this, you would either have to copy them through like an FTP or ship hard drives, depending on how large the data is. In this case, the third party was actually in the same cloud provider as us, and rather than copying data and whatnot, it became just a permissions exercise. And so literally within a couple hours, we were able to access their data. So once they gave us access, all of a sudden, all of our tools and all of our databases and our VMs and users could now access this data. We could run all or at least similar queries and explore that data. And that really greatly increased our agility there. And again, because they're in the same cloud provider, we could use a lot of the tools we were familiar with. So we used AWS Glue, we used Athena, and we were able to explore and walk through the data. We used Redshift and Redshift Spectrum because their data was in S3, so we were able to import it in Redshift and do some bigger processing there and a bit of experimentation with Redshift. Once we found the data sets that we wanted, we could then filter them and package them into nice little things that we could then ship off to our where all of our other analysis tools were. So in this one, we were shipping them off to BigQuery. This was highly efficient in that we could send much smaller packages that were already set up and filtered, and it cost us a lot less to transfer the filtered data over to the cloud provider. And again, we automated all this. We had it running on a schedule with Lambda that was just triggering these jobs and shipping them off to BigQuery. And from here, I'll pass it back to Sarah.
So when we got this new data, one of the biggest upsides to it was, of course, this idea that we had more data points, and more data points means that we can look at more regions and have more analyses. So a good illustration of this is the increase of regions that we can look at. So here on the left, what I'm showing is an interregional mobility graph. So an interregion mobility graph shows the percentage of people traveling between any two pairs of regions. And here I'm showing interregion mobility between provinces. So for our original provider, you can see that there are a lot of blank squares in this graph. You know, between Alberta, for instance, and Newfoundland and Labrador, we didn't have enough data to fill anything in. And there's, you know, between Alberta and Prince Edward Island, same thing. So there's a lot of blank squares here. But then if we move to provider number 2, this is the same graph, basically, with the same province to province mobility for the same sort of time period. You can see that we've filled in a lot more squares. So the middle diagonal will always be blank in this type of graph because it represents movement between a region and itself, which is not what we're looking at here. We're looking at region to other region. But as you can see here, we have data between Alberta and Newfoundland and Labrador, or Alberta and Prince Edward Island. So we've been able to fill in most of the squares in this graph. So that increase from 250,000 users to 400,000 users really allowed us to sort of study more regions by having that denser data. This denser data also allowed us to look at more point of interest locations and also look at point of interest locations over time. So one of the analyses that we did with this sort of data was long-term care facility analysis. As you're probably aware, at the beginning of the COVID-19 pandemic, a lot of the deaths happened in long-term care facilities or seniors' homes. And we postulated that the cause of the spread between these homes was workers that were moving from one home to the other. So one way to try to capture that network, or that network effect between homes, that linkage between homes, would be to look at which crowdsourced devices we could see that were in one home during, say, a given week, and that we also detected in other homes during that same week. So with that more thicker data source, we were able to do that and detect more of those interactions. So what I'm showing here on the bottom is a map that shows seniors' homes, long-term care facilities, seniors' homes around Toronto. And if the seniors' home is green, that means that during this particular week, we detected that there were less than 5 devices that were present in that senior home that was also present in another senior home in that week. Whereas if it was yellow, there were 5 to 10 devices that were detected in that senior's home that was also detected in another senior's home that week, indicating that there's more risk of transmission, inter-facility transmission in a yellow area. And of course, if there were being red ones, that would be more than 10 interactions that we detected in our data set. And that also allows us to create these sorts of network graphs that you see in the upper left. And this sort of shows how these seniors' homes are linked together. So it shows that, for instance, you might have a cluster of seniors' homes like the one on the bottom right of this particular graph, which shows that you have sort of 5, 6, 7, 8, 9 seniors' homes that are in this cluster, with the red ones indicating the ones that have had COVID cases. So these 9 seniors homes are all linked together by individuals who move between these seniors homes. And this is during July. So this is after the government had asked them not to have interactions like this. So this sort of network graph serves 2 purposes. One, it allows you to seniors homes that they still have, or long-term care facilities, they still have this sort of interaction going on. And it allows you to identify these sorts of choke points of homes that have a lot of these interactions, and maybe talk to these homes and ask them to do something about it. The next sort of analysis that this new data source allowed us to perform was outbreak analysis. So when we talk about outbreak analysis, what we want to see is how people move from outbreak areas. So if you look at the devices that you can find in an outbreak facility, you can then look at where those devices travel to in the next few weeks. So the graph at the picture at the bottom here shows an analysis that was done following an outbreak in Alberta. So you can see that in the 2 weeks following that outbreak, devices that were detected in the outbreak facility basically went all over Canada. And the brighter, in this case, the trace on the graph, the more device activity was detected in that particular region. So this also helps public health sort of warn regions where they may be at an exposure risk from people moving from outbreak regions into their communities. We can also use outbreak analysis or these sorts of data sets to monitor whether or not high-risk groups are following public health guidelines. So people moving from outbreak sites may be asked to quarantine, or may be asked, certainly when they're moving into the Atlantic bubble, for instance, they should be quarantining. Are they? Well, with this sort of data, we can have some insight into whether that is happening or not. So after we've been working with the data from provider number 2 for a while, we noticed that we still had some issues. Of course, the primary issue was that the number of users at 400,000 a day is still insufficient to do this analyses we wanted in rural and remote areas. 400,000 users, again, sounds like a lot of users, but if you want to do analysis at a very local location, so if you want to look at the number of users in CARP, the sort of movement in a CARP or in some small town, you're not likely to have enough hits in that small town to make a statistically significant finding. Furthermore, we had a problem with an unstable user base. So what I'm showing here again in the bottom left is a graph that shows the number of users from this provider number 2 who had been in that data set for more than 45 days or longer during the period that we were looking at, because you sometimes have a lot of users that come in and they come out for a couple of days and they're not too useful for analysis. So what you're seeing here is that around the time just after we were sent home, things closed down, there's a big dip in the number of users, and then the number of users comes back around April 26. What's happening here is that the way that this crowdsourced data is usually collected is through apps. And when you collect through apps, sometimes the app providers, they lose track of those app providers and they lose a set of apps, and therefore they lose a set of data for a period of time. And that's what we confirmed happened here with provider number 2. The problem with this is that it introduces a lot of bias. If you can think about trying to capture the movement or how Canadians move, the best way to do it would be to randomly select Canadians. Well, we're not doing that. A better proxy, a fairly good proxy for Canadians would be Canadians who use cell phones, because almost all Canadians use cell phones. But we're not doing that either. We're getting data from cell phone users who use certain apps, and apps will have a user base, right? The people who use a fitness app will not be the same people who use a grocery store shopping app or list app, or the same people who use a gaming app. So each of those apps have a demographic user base. And the people who collect this sort of crowdsourced data try to make a suite of apps that will have a user base that is fairly representative of Canada or Canadians. But when they lose a large chunk of their user base like this, it's not like they're losing a random 1 out of every 100 of their users. They're losing a set of apps, and that changes the demographics of who they're looking at. And that makes their bias even worse. And you can see that on the on the right-hand side in this graph that I'm showing, which is just the percentage, is the sort of activity that we're seeing in grocery stores. So if you compare here, this is provider number 1 and provider number 2, and you can see that up to the point where there's this dip in users in provider number 2, they're fairly congruent. You know, they have the same sort of pattern, and then suddenly there's a big dip in provider number 2 and the number of people going to grocery stores, while provider number 1 has not got that same dip, and then they come back up right when they have the users back. So like this is not actually reflecting user behavior. It's reflecting the fact that the apps they lost, probably the demographics of the people they lost were more of the grocery shoppers of the household. And this means that it's very difficult for us to use the provider number 2's data to compare month to month, because this is because of the unstable nature of the user base. So we were looking for even better data with less bias and more users, and we hit Paydirt when we were able to get an agreement with an operator, one of Canada's cell phone operators, to get some of their anonymized cell phone data. And this represented 10 to 11.5 million unique users with persistent IDs, and of course was less biased because it represented just straight cell phone users with no app intermediary. But the caveat that comes with that data is that the geographic resolution is not as good as crowdsourced data. Instead of getting a read of exactly where a user is, their lat long, you'll get a read of where the tower is that they connected to, so the closest cell phone tower. So the error on that is a lot more than getting the lat long of the user. Now, when we got that operator data, now we were talking about really big data. So we were talking 40 terabytes or about 95 billion rows a month. And that's more data in a week than what our crowdsourced data sets were. So this was stored in the cloud in BigQuery, and moving that size of data over to our cloud was not practical. And so we had to set up a way to get to that data and to comply with the strict access and regional requirements that the operator insisted on. So I'm going to hand it back over to Neil, who will explain how we did that.
All right, so again, this is where our cloud architecture came in handy, the flexibility of our cloud. We did something very similar to what we did with Public Health Agency. We took our environment and we basically duplicated it. This time, the regulations from the operator were that we had to reside in Canada. All the data could only travel through Canada, and users could only travel through Canada. Users had to have, if they were to remove any data from the environment, it had to stay on encrypted drives, and the access to those environments had to be highly restricted. Users had to have a certain amount of security clearance and limited access. So again, we did the same thing. We took our system, which is mostly done in infrastructure as code, and we redeployed it into the Canadian region. This time we actually duplicated the firewall and we highly restricted the access into that region and created a new VPN with MFA users that were coming from Canada only. And then from there, we made a template of a VM that had encrypted drives, again with restricted access, and we deployed that to about a dozen of our data scientists. From there, we were able to create an IP address that would connect to via VPN into the operator's environment, and the operator could then whitelist that one IP, so they would know that anyone coming from that IP was coming from our restricted environment. And from there, we could then start exploring their data. And so we could then access their data through their own environment, and we could then do our exploration and all of our research that way. And that's all I have to say about that, and that enabled our researchers quite nicely. Oh, and one more note is we actually deployed this in, I say under a week, but I think it was actually closer to 3 days. And the funny thing, the paperwork and to sign all the agreements and NDAs and stuff took longer. So deploying this environment was much quicker than actually getting the access. And with that, I'll pass it off to Sarah.
So what did the operator data get us? Well, the operator data allowed us to do primarily the mobility analysis at much more fine-grained geographic regions. So not only national, provincial, large cities, but national, provincial, city, census subdivision, health region, or even neighborhood analysis for both regional mobility and interregional mobility analysis. Because the operator data does come with the tower location and not the user location, we cannot do the sort of point of interest analysis that we could do with crowdsourced data. So that is not supported with this sort of data. But we can do outbreak dispersion, and we can do what's called capacity analysis. So we can look at, for larger outdoor spaces like parks, and if public health decides that, you know, there should be about 1,000 people in that space in a certain period of time, given that we have a quite large percentage of people in our data set, we can extrapolate and figure out whether or not a number of people in that space was reasonable. So I'm going to go over a few lessons learned from the work that we did. One of them is controlling costs, because we want to make sure that we're not overspending. There are a couple of different price models that we ran into in the cloud, one of which is the cost per terabyte queried. So this is the way that our internal BigQuery is set up. So the standard cost per terabyte queried is usually for BigQuery is $5 per terabyte. And you know, that sounds reasonable, but if you've got hundreds of terabytes, you can quickly run up a quite big bill if you're not careful. So what we tend to do is make sure, of course, that you're only selecting the columns that are required for your query. So even if you've got a big table with hundreds of columns, if you only select a few columns, that it's only those columns that you selected that will count towards your query count, the gigabyte count or the byte count for your query. Another thing that I do quite a lot is create subsets of data to try ideas. So, you know, we have this huge 40 terabyte data table. It's often easier to create a 1% sample table or something like that, and then use that to test things out. And then once you're sure that you've got what you want, then you can create run the query against the full table. We also create aggregate tables of data that we query often or that we know that we can aggregate down. An example of this is sometimes we have a lot of events coming in, and we can aggregate those into the events to look at the events that we really want, which is, you know, when people move, right? So if there's a lot of intervening events there not indicating any movement, we can remove those and just keep the times, you know, how long somebody has been someplace between movements. And of course, we use this handy dandy thing from BigQuery that shows the query size preview. So at the bottom here, I'm showing a query that I was running to calculate the percentage of national movement, and it'll show at the bottom that it's going to run 23.7 gigabytes. It's going to query when it runs, and that will cost me about 11 cents, which for a query that I want to run every day seems quite reasonable. But if you check this before you run something, it'll give you a little sanity check. Am I going to be running this against 100 terabytes? Okay, do I really need to run this query? Sometimes yes, sometimes no, but you should be aware of how much it's going to cost. The other model that we've run into is a flat cost for set compute. So for an example of this is a Redshift cluster in AWS, and we did have a Redshift cluster in AWS at one point for this project. We ended up not using it as much, not because it was more expensive, but because there were some problems with the GIS implementation in AWS that made our queries quite slow. In this case, you're paying for the size of the cluster, right? You scale out your cluster, and then you've paid for that size, and then they cost what it costs, no matter how many queries you run. So you want to scale your cluster carefully, make sure that you're not overpaying or underpaying. You know, if you're underpaying, you're just waiting too long for your results. And then you have to be aware that you're sharing that compute and competing for that compute with others. So you may want to arrange with the other people in your group to make sure that if you've got queries that have to be completed for a certain deadline, that you're not stepping on each other's toes. And you have to manage the uptime of the cluster with the other people in the group so that you're not running that cluster overnight for no reason. For both models of query costs, there's also a cost for keeping data. So you have, usually when you do a query, if it's a small amount of data that comes back, you can just keep it in a temporary table. But if it's a lot of data that's coming back, they'll have you dump it into a results table. And you know, if you're not careful, those results tables just grow and grow and grow and grow and grow, and then you've got tons and tons and tons of results tables, and they're not going anywhere, and you're just paying for storage costs. So best practice there for us is to set expiry dates on data sets. So if you've created the results table and you want it for a couple weeks, then you put an expiry date that says it'll delete in a couple of weeks. And the other thing is to use meaningful names on your data sets. So we often have a place called test where we put things that we're testing. So results of test queries, but we try to give them still names in there that mean something. So not something like this one I'm highlighting, which is in test, and it's called test different data set. And it was created, it's 44 gigabytes. It was created October 9th, 2019. I have no idea who created this or why they created it or what it means. Should I delete it? Is it useful for something? I ended up deleting it. If somebody's angry at me about it, they'll come and talk to me about it, but really they need to name their data sets better if they want to keep them, because I have no idea what that means. So the other thing is that we were using a lot bigger data set than we had previously as far as computing over that data set at one time. We had previously worked with a lot of big data, but we were not usually running queries over, you know, hundreds of terabytes in one shot. BigQuery is meant to do this sort of processing, but even BigQuery will choke at times, and it will come back and it'll say it's run out of resources. So this will usually happen when you're asking it to sort data. So there are a few ways you can get around this. One is just not to sort your data. Another way was to use intermediary tables. So if we had queries where you needed to sort, and sometimes you do need to sort, you can sometimes break up your query and then store intermediate results in tables, and then that will get your query to run. And the third way that we would do it would be to break query groups. So if you're doing a query that calculates something for every day of the week or every day of the month, sometimes you can just, you know, we'll just run that query for the first week and then put it into a table, and then it's the second week and append the results in the table and keep on going like that, and that'll get it through without running into this out of resources problem. The other thing with big data is that running queries on those large data sets takes time. So unless you want to spend all your time just staring and waiting for the query to return, which is not very efficient, again, those sample data sets, those sample data tables, I would create them with 1% or 0.5% of our data, and we would use those to quickly build and debug queries. And then we would run the debug queries in batches from scripts and run those overnight. And then when I got in the morning, I would have results. I could look at those results, play around with them, play around on my test tables to refine anything, and then run it overnight again and come back to results that I wanted to look at again the next morning. So now I'll hand it back to Neil for closing remarks.
Okay, well, I think it's pretty clear that the work that our data scientists were able to pull off in such a short time was pretty amazing, and I really just want to not take all the credit, because they obviously worked very hard too, but we did have an environment that enabled them to work fluidly, let's say, and we really think that the VRD is one of these tools that really helps scientists. They're only as good as the tools they have, and we think VRD is one of those tools. It was built to enhance discovery science again. So I've said this before, but this is definitely different than an operational or regulatory or production environment. It's just a different approach where we give a lot of flexibility and a lot of leeway, and it gives you a lot of agility. And so agility in the cloud lets you do all kinds of different things, like going to where the data is, like in the examples we've shown, and choosing the right tools for the job, especially being multi-cloud and most environments have lots of different tools. So closing notes was just the agility is really what enabled our researchers to do a lot of the amazing work. And I just wanted to close on that thought, and that's the end of our presentation. So I believe there's going to be a chat on the side here, and we can start taking questions right away. Thank you.